Okay, so we are in this book right here, Causal Inference in Statistics, and we are on the final question of Chapter 3, which is question 3.8.1. Okay, so what we have is a DAG here, and it's accompanying equations. Okay, so let's just make sure that we understand how these two things tie together. So these equations describe the graph, or conversely, this graph describes all of the equations. Okay, so let's just look at this. So z1, notice that z1 doesn't have anything affecting it. Okay, so the value of z1 is z1. Now we also assume that all of these variables have their own error term, which isn't shown. So z1 should just be its error term, and that's what we get. z1 equals u1. And again, u1, the error variables are not shown. Okay. So let's go to W2 here, or I'm sorry, W1, and let's try to predict what the equation for that would be. Well, we see that W1 is affected by Z1 via A1. So probably W1 equals A1 times Z1 plus the error term for W1. So if I go and I find W1, that's in fact what we get. We get A1 times Z1 plus the error term for W1. I'm not sure why this prime is there. I think that might be a typo since it's the only coefficient with that little prime symbol there. So I'm just going to assume that it's an error. Okay. Now we could get even more complicated. So let's look at x. So let's try to predict the formula for x. Okay, well x is affected by W1 via T1 as well as by Z3 via T2. So I'm going to guess then that x equals W1 times T1 plus Z3 times T2 plus its own error term. And we go up here, and that's exactly what we get. Okay, so that's how these things are related. So we're going to use this model to answer a bunch of questions. Okay, so the first one is we're meant to identify 3 testable implications of the model. Now, there are many more than 3. I think I counted somewhere around 20. But we're just going to do a few, and so your answers may differ obviously from mine. Okay, so what is a testable implication? Well, generally these testable implications come out of conditional independencies in the data. So in other words, we look at 2 variables that are correlated, and then that correlation goes away if I condition on the correct set of variables. Okay, so let's look at one of these. So we have W1 and W3, right? So here to here, these are correlated, or the DAG predicts that they should be correlated, right? You can look at this in the data, but they should be correlated if the DAG is correct, or at least correct in this in this bit here, because W1 affects X affects W3. Okay, so that means if I condition then on X, I should render W1 and W3 independent of one another. Okay, so that would be a testable implication. I can look to see if W1 and W3 are in fact correlated, and then if that correlation goes away after I condition on X. Okay, so that would be a testable implication to see if the DAG is correct. All right, and so here we have exactly that. Okay, so that's one of the answers that I gave. Okay, now notice what we cannot find conditional independencies on, right? We could not use the connection between X and W3 as a testable implication, right? Because there's nothing we can condition on to get rid of that correlation if the DAG is correct. Okay, now that itself might seem like a test, but the problem is that there's always the risk of there being omitted variables. So even though we have X affects W3, it could be that there's other, intervening variables in here, in which case our DAG wouldn't be perfectly correct. Okay, so anyway, so I'll let you kind of look at others for yourself. But another way that I believe we can go is to induce a correlation among uncorrelated variables here. Okay, so let's look at an example of that. Okay, so I have Z1 and Z2. Okay, now these are just all by themselves. If we do nothing, these should be, if the DAG is correct, uncorrelated. Okay, because there's a few paths that we could get from one to the other, right? So we could go Z1 all the way down to X up to up to z3, but the problem is that x is a collider, right? And if we don't condition on x, then it's closed. So that path is closed to us. Okay. We could go z1, z3, z2, but z3 is a collider, right? So we can't go up that path. Or we could go z1, x, y, z2, but now y is the collider, right? Between w3 and w2, right? So these should be independent. Therefore, if I were to condition on, say, z3, I should open up this collider and induce correlation between the two. So I believe that that should be a testable implication as well. Okay, so I'll let you look through, do your own or verify the ones that I have here. But the other part of, this doesn't ask us to do this, but we want to know how could we test these. How could we using linear regression, how could we test these things? Okay, so for this first one here, again, what I'm trying to do is determine if conditioning on x makes w1 and w3 independent of one another. So what we could do then is we could regress w1 on both w3 and x. Okay, and if the DAG is correct, then the beta coefficient for w3, which is basically it's kind of like the correlation, not necessarily, but it's the association between the two variables, then that variable should go to 0. And what I've done here is I've set beta, or I put this superscript 0 to denote that it would be this coefficient that goes to 0 if the DAG is correct. Okay, and so again, you can go through these for yourself and just make sure that you understand the logic I just went through. Sorry for skipping so much here, but this is a pretty long question. Okay, part B, identify a testable implication assuming that only x, y, w3, and z3 are observed. Okay, so this is really not that much more difficult than the previous question. But we just need to make sure that whatever we are, whatever variables that we're using are in this set right here. Okay, so we'll just kind of go to the top one here. So w3 is independent of z3 given x. Okay, so if I go up here, so I'm saying that w3 is independent of z3 given x, and these are 3 of the variables that we have that we observed. Okay. And so we see that z3 is in fact associated with w3 via x, right? There are other paths, but all of those other paths are blocked at the collider at y. Okay. And so just with the variables that we have to measure, so if I condition on x, then I should get that z3 and w3 are no longer correlated. And again, how can I test that? Well, I can test that by regressing w3 on z3 and x. And if the DAG is correct, then the beta coefficient, the regression coefficient for z3 should go to 0. Okay, and you can check the next one for yourself. Okay. Now in part C here, okay, now what we need to do here is for each of the parameters. Okay, and here parameters refers to these little coefficients on the paths, a1, a3, etc., the lowercase letters. We need to write a regression equation in which one of the coefficients in that regression equation is equal to that parameter, and then identify parameters for which more than one such equation exists. Okay, so I think the easiest thing to do here is to just give an example. I think that wording is maybe just a little bit of word salad. So let's start here on a simple one with A1. Okay. So we want to write a regression. We want to write a regression equation wherein one of the coefficients of that regression equation is equal to A1. Okay. All right. So if I regress W1. Or, if I try to make a model for W1, right, because A1 is feeding W1, well, my regression equation should be W1 equals Z1 times A1, plus an error term that I'm just going to ignore here. Okay. So that would be my regression equation. Well, in this case, the beta coefficient for Z1 is A1, right? So normally when you write a regression equation, you're using these betas. I think the book uses R as the regression coefficient, but beta is more common. It doesn't really matter. And so here, beta Z1 equals A1. Okay, so hopefully that's obvious how that's happening. Okay. So I've gone through and I have an equation for each of these, for each coefficient. So you should go through and check those out. But we're also asked to identify parameters for which more than one equation exists. Okay. So there's actually quite a few of these, but many of them are inconsequential. Okay. So let's see, what did I use as an example here? Okay, yeah, let's go back to the one that we just did for A1. Okay. Well, so here's my equation for A1, or I mean for W1, but from which I can solve for A1. Okay. Well, if I were to regress W1 on just some inconsequential variable, such as W2 or something like that, right? Now notice W2 is not connected to anything over here, right? Because it can't go this way because it's blocked by this collider, and it can't go up through Z2 to Z3 because it's blocked at Z3, right? So it has no, nothing to do with what's happening on the other side of the DAG here. But so I could regress W1 on Z1 and W2 and still get a valid estimate for A1. Okay, but those aren't really the interesting cases here. So let's find an interesting case. So let's look at let's find T1. Okay. Well, so here's my answer, my initial answer for finding T1, and so let's just reason through it. So T1 feeds X, and so I'm probably going to regress X onto other variables. And what should I regress it on? Well, probably W1 and Z3, because those are the things that are feeding X, and they're feeding X through T1 and T2. So my regression equation for X would probably be beta W1 times W1, where the beta W1 equals T1. Okay, I hope that's making sense. Okay, so we have that. As well as, so plus Z3 times beta Z3, where beta Z3 equals T2. Okay. Now, if I was just concerned with finding the coefficient for T1, I could regress on something different here, okay? So the idea is to be able to close, I shouldn't say close, that's not the right word, but I want to be able to somehow capture, everything that's affecting X, okay? Now let's say that we couldn't measure Z3 for some reason. All right. Well, one thing that we could do is to measure instead Z2. Okay. And now we would have a beta coefficient, beta Z2 times Z2, that would represent this entire path. So beta Z2 would not necessarily represent B3 or T2, right? It would be a combination of them. Okay. But nevertheless, we account for the path coming into X via Z3, right, by condition on Z2. And then if we also condition on W1, well, then the coefficient for W1 is still going to be equal to T1. Okay, so that's, yeah. So there's my answer for that. Okay, so there's a couple other examples, but I'll leave it there. Okay, so now we get into some of the very interesting stuff. Okay, so in our DAG, we're going to assume that we only can measure X, Y, and W3. Let's just see what those are. X, Y, W3. So this bottom row right here. Okay. So we want to know which parameters can be identified from the data. And we also want to know if the total effect of X on Y can be estimated. All right. So, so we're going to do this in a couple of different ways. One is we're going to use just kind of the material in the book to deduce the answer, okay? But some of these get a little bit tricky. And when it gets tricky, it's a nice thing to try to do to simulate the data. Okay? And so we're also going to do simulations. So what I have here, what I have encoded here, okay, is just this, is just these equations. Okay? So I have the equations for each of the variables, right here. Z1 just equals its own error term, and so its own error term is given this. And then all of the parameters that come off of Z1, I'm defining values for them. Here I'm calling it 2 for A1 and A3 equals 3. Again, I'm assigning these, and the reason I'm assigning these is because when we go through and do some simulations, I should be able to recover the correct values for A1, A3, and all the other parameters. Okay, so we're going to run that. Oh, and also I have n here, and n means the number of samples that I'm going to generate from my data set here. Okay, so that's running. So now when we only have W3, X, and Y, then the only parameters that we might hope to be able to estimate are the ones that are somehow associated with those, so C3 and A. Okay. Okay, so first let's just use our powers of deduction and the rules that have been given to us by the book here. And we should guess that that C3 is estimable, and we should be able to deduce this based on what the book calls the regression rule, and that is discussed on page 84. Basically, what this says is if we remove the edge C3 between X and W, then we get a modified graph. And so I'm just calling that G sub C3. So now in that modified graph, okay, so what's the modified graph? The modified graph is this with C3 deleted, okay? So in that graph, W3 is deseparated from X, okay? So we need to regress W3 on X, and that should give us an estimate for C3. Here I've just put W3 equals C3 times X, but we could just call this beta X, okay? And so C3 is just the direct effect of X on W3. Okay, so what I'm going to do to try to simulate this is so if you're not familiar with R, hopefully I can give you enough of an overview here, but I'm creating an object, and that object is a linear model using ordinary least squares, and that's what this command here does in R, of W3, right, which I've already defined here, okay, and I'm going to regress it. That means, regress this thing on whatever is over here on X. Now there's also a 0 here, and that is because in R, R assumes that there's also an intercept. So it adds another parameter in there, but we don't want that parameter, okay? So, so now when I run this, I'm going to get the estimated coefficient for X, and it should equal what I've set to C3. And what have I set C3 to? I've set it to 2. Okay? So when I run this, so we get that the coded value for C3 equals 2. Okay? And that's correct. Now, it's by definition correct. And now the estimate for C3 equals 1.99. So basically 2. Okay? So so that gives us confidence that we can, in fact, estimate C3. All right. So now let's also do the same for A. All right. So if I come up here, okay, so here's A. If I use what again is called the regression rule, if I sever this connection, so if I omit A from the graph, okay, what do I need to condition on to make sure that W3 is deseparated from Y? Well, I could condition on X, and we get to observe X, therefore that's just fine. Okay, so if I regress Y on X and W3, I should get an estimate for A, or a proper estimate for A, an accurate estimate for A. Okay, so so that's what I'm going to do. So I'm regressing Y on W3 and X. Okay, and I'm going to get the estimated A for it. Okay, and so when I do this, so it says that the hard-coded value for A is 3, right? So I hard-coded that up here. Where is A, by the way? There it is, 3. Okay. And the estimate equals 1.82. Okay, well that's puzzling. So what is going on here, right? That seems quite a ways away from the hard-coded value of 3. Well, roughly what is happening is that X here actually is a fairly complicated object, right? Whereas W3 just has one thing coming into it, namely X. Okay? X has a bunch of things coming into it, all right? And what is going on is that the values for X are more variable, again, because it has more inputs coming into it, okay? And so, so what is happening actually is our estimate is poor, but the estimate is poor is because we have too small of a sample size given the complexity of the situation, roughly speaking, okay? So here I have n equals 100. Let's see what happens if I go up to n equals 1,000. So I'm going to regenerate new data, okay? And notice that if I run the previous one, I get even closer to the true value, which is 2 for for C3. And now if I come here and I run this, now I'm getting closer. Okay. Now the estimate is about 3.08. Okay. And again, that is a function of taking a larger sample size. Now that can be rather intimidating because we're being told that we can get a valid estimate in this case for what is it for A. But with 100 data points, we might have a very poor estimate for A. Okay. So I'm going to generate some new data, 1,000 new data points by rerunning that block, and let's just see what happens. Okay, so our first one, again, we get a good estimate, and here we run it, and now it's 2.63. So you see how much this estimate is jumping around. Okay, so what do we need to do? Well, I guess that we need more data, right? So now I have 10,000 data points here. Okay, I run it, and predictably, this one does very, very well. And what happens here? We're getting close to 3. Now let's just generate some more, another 10,000 data points. Run it again, and now it seems like maybe we're settling down, close to a decent estimate. Okay, yeah. So with 10,000 data points, we get we might trust our estimate here. Okay, so there's a lot of very interesting things to be said about the rate at which we expect this estimate to converge, but we don't need to get into that right now, other than to say that sometimes, even though by the principles of what's going on here, we can get an estimate for this or that or this or that, sometimes data is noisy enough that it is not very easy to do, or that our estimates might not be all that trustworthy. And that's where things like standard error of the estimates and all those things come in. But this book isn't talking about, and so I'm going to kind of leave it there. Okay. So what about the total effect of x on y? Okay. Well, in one sense, we already know that we can estimate this, and the reason we know that we can estimate is because we've done it before. Because that that particular configuration it lends itself to the front door method. Okay, so I believe that's question 3.41 if you want a little bit more with that. Okay, but let's see how we might get that here. Okay, so notice that we can't just simply regress y on x, right? We can't just use this thing right here. Okay, and well, so let's do this. Okay, so the correct value should be A times C3. There's an error there. Okay, but what I'm getting if I just regress x on y is I'm getting a value that's not correct. Okay, so instead what we need to do is we need to just simply multiply our previous two estimates. Okay, so when we do that, then we get fairly close to 6. Okay. It's interesting to know why we can't just regress x on y and get the total effect of x on y, but we can take our two separate estimates for for A and C3 to get to get the total effect. The reason is because if we come up here, if we're at x, okay, then there's this backdoor path that goes x, z3y, and so when we regress y on x, we're getting both of these paths. We're getting this path as well as this non-causal pathway. Okay, so that's why we can't just regress y on x and get the total effect of x. Okay, where are we at here? Okay, part E. Okay, we're asked if we regress z1 up here on all other variables in the model, which regression coefficients, that should be coefficients, will be 0. Okay, so so here we have z1, and we're going to regress it on everything. So our regression equation would look like this right here. Okay. Now when we do this, okay, so when we how do I want to say this? So we condition on W1, right? Well, when we condition on W1, then X here is no longer connected with Z1. It is de-separated from Z1. So the coefficient then for X should go to 0. Okay, so that should be one of the coefficients that goes to 0. All right. And similarly for so maybe I'll let you go through these just to cut down on the time of this video, but these following coefficients should go to 0. Now again, we can simulate this. So I'm going to regress Z1 on everything and then look at the coefficients, okay? And then and here, these things right here, this just kind of gives me a printout. So again, if you're not familiar with R, don't worry about that. The important bit is that we're regressing everything, and we're going to look at the coefficients, okay? And so when I do that, so I've said that beta W2, W3, X, and Y should go to 0. Okay, so we have, let's see here, so we have beta W2 is close to 0. Again, the problem is often sampling error. Okay, W3 is 0, beta X is 0, beta Y is 0, and the other ones are non-zero. Okay, which is what our DAG would predict. Okay. All right, part F. So the model in figure 3.18 implies that certain regression coefficients will remain invariant when an additional variable is added as a regressor. Identify 5 such coefficients with their added regressors. Okay, well this is pretty basic. All that we need to do is to find it. So I've only done 2 here because I think it's simple enough that we don't need 5 to make the point. But we just need to find a regression equation. Okay, here is W3, and then just find another variable that is de-separated from the outcome given what it's already being regressed on. And so in this case, I'm denoting this superfluous regression regressor variable by putting it in parentheses with a little star here. Okay, so for example, for W3, I'm saying that if we add W1, then it shouldn't change, shouldn't change the coefficient for beta X. Okay, so so if I go here, so W3 is being regressed on X, and if I add W1, well, W1 is already de-separated from W3 via X. So the regression coefficient for X shouldn't change. Okay, so so let's look at my 2 examples here. I also have one for Y, but we could test this if we run the regression here for W3 on X, and then as well as X plus W1. And in this case, the coefficients for X should not change, and also the superfluous one should go to 0. Okay, and there's also the one that I've predicted here for Y. Okay, so we do this. In fact, just to clean this up, let's just look at this top one here. Okay, so when we just regress W3 on X, we get an estimate of 2. Okay, and when we add W1 to the mix, X remains 2 and W1 goes to 0, which is what we should expect. Okay, and now if doing the same thing for Y, again, you should work through this for yourself here. but we'll just look at the simulated results. Okay. So here, x is the superfluous variable, and sure enough, it goes to 0. Okay. And then the ones that are not superfluous, w3, z3, w2, they have coefficients of 3, 3, and 4, and they remain 3, 3, and 4, after adding the superfluous variable there. Okay. And so you can, yeah. So anyway, you can do that for 3 more if you would like. All right, part G. Assume that variables z2 right here and w2 right here cannot be measured. Find a way to estimate b, this guy right here, using regression coefficients. Okay, and then it gives us a hint, which is to find a way to turn z1 into an instrumental variable for b. Okay, so this one is not straightforward at all. I mean, you can certainly work yourself there, and if you're very familiar with this stuff, you could get there. But it's reasonably difficult. And so I'm going to try to talk through it, but there's some equations that are mixed up here, and you're having to refer to equations. So I really suggest that you come through and read this and try to piece it together for yourself. Okay, but let me try to give a verbal overview here. So first, let's identify the problem. Okay, so if I'm trying to find the effect of z3 on y, that's not the right way to say it, because z3 has 2 paths getting to y, but this path right here. The problem is that there's a back door open, right, which goes z3, z2, w2, but we're told that we can't measure z2, w2, and so we can't close this back door path. Okay, that's what the problem is here. Now, in the book, we're told that we can use a variable as a instrument, and we'll talk about that, what that means here in a second, if in the graph G alpha, that variable, and here in the book it's just called x, but we should be calling it z1, the one we want to nominate as an instrument. So x, or z1, can be an instrument if it is d-separated from y in the graph G alpha. So here G alpha is where I have, I've taken out the edge from z3 to y. Okay, sorry, I have misspoken here. Okay, so a variable can be called an instrument, so z1 can be called an instrument if it is d-separated from y, okay, in the graph where I omit that edge, here b, okay, and it is d-connected to x, and here x refers to z3, right, the effect of x on y. Here we have the effect of z3 on y, Okay, so we can use z1 as an instrument here. Now, this threw me for a little bit of a loop because I made a very naive mistake, which I was thinking that because of the example that's presented in the chapter, I was trying to find a way to make z1 be an instrument for z3 that would give me b. But the problem is that, like I already said, z3 has 2 causal paths to y. We have b, then we have t2, c3a, right? So z1 becomes an instrument for the total effect of z3, right? So z1 can become an instrument for both b and then t2, c3a. Okay. Now notice that z1 does meet the criteria of an instrument. Okay, if I get rid of b, it is d-separated from y, right? Because it can't go down this diagonal path, right? And it is d-separated by this path, okay? z1, w1. Oh wait, it's not separated. It's not d-separated. But how can we make it d-separated? Well, if we additionally regress on w1. Okay, so you can see how many moving pieces are to this to this answer. So z1 can be an instrument for the total effect of z3, which includes 2 causal paths, if I additionally condition on w1. Okay, so now notice what happens when we regress y on z1 and w1. Well, what we get is So this is okay. So what we get then is the total effect of Z3 times A3, right? Because we've closed down this connecting path. Okay. And so when I condition on y on Z1, then what I get is I'm accounting for this path, which includes B, as well as this path, A3, T2, C3A. Okay. So that means that that means that if I regress y on Z1 and W1, then my coefficient for Z1 is A3 times the total effect, that tau, for Z3, which again includes both B and then T2, C3A. Now, we can get an estimate for A3, right? Because that's just regressing Z3 on Z1 there, okay? So and here I'm just going to call it gamma because now I have a beta Z1 and a gamma Z1. Okay, so that way I don't have two beta Z1s. Okay. And so now if I want to solve for the total effect of Z3, tau Z3, I'm sorry that those look like the same size. The Z3 is actually a subscript, but this is just the way it renders. I can solve for the total effect of Z3 by dividing beta Z1 divided by gamma Z1, right? So here's my total effect of Z3 equals this. Okay, but also tau of Z3, the total effect we've already seen is, B plus the other path. Okay? All right. So now what we have is this expression, and now we can solve for B by taking, this other path, this non-B path, T3, C3A, to the other side, and then we see that B is beta Z1 divided by gamma Z1 minus T2, C3A. Okay, so I'm sorry for the convoluted answer, but it is a convoluted answer. And so, like I said, you should really work through with paper and pencil, and hopefully I've laid the steps out clearly enough that you could work yourself there. Okay, now, fortunately, we can also get estimates for T2, C3, and A, right? And we've done this already in the first part of the question, right? So we can get T2 through this expression here, C3 through this expression, and A through this expression. Okay, so now we can estimate everything in here, and therefore get a expression for B. All right, so let's do that. Okay, so here I'm getting the regression coefficients for beta Z1 and gamma Z1, right, with the appropriate regressions. Okay, regressing y on Z1 and W1, which we talked about. And then to get A3, then otherwise known as gamma Z1, again, sorry, hopefully you can work through it with pen and paper, then we want this regression. So now we have these two parts, right? So I'll divide this by this to get that. And now, in order to get the estimates for T2, C3, and A, I run the corresponding regressions. Okay. And now, my estimate for B is the division of the beta and gamma minus my estimates for T2, C3, and A. Okay. So I've set the value for B to be whatever it is. In fact, let's look what it is, just to cut the suspense. What is B here? B is 3. Okay, so hopefully we're getting something close to 3. And then we'll get our estimate, which is all of this right here. Okay, so we'll run all of that. And it's not bad. Okay, it's not bad considering how many little estimates we had to make along the way, right? So every one of these regressions is showing, it has not only its own error term, right, but the error term of everything that predicts that particular variable, right? So everything that we're doing is introducing error, and we come up with a decent estimate. Now again, this is really a sampling problem. So here we're at 10,000. If I go to 100,000, presumably this gets better. We'll see. Presumably this gets better. So now we're getting better. Okay, now I hesitate to go up to 1,000,000 because it starts to drag on the computer. But anyway, that is how we could get an estimate for B. Again, notice that that when these models get sufficiently complex, and this isn't even a terribly complex model, but when we're having to go through and estimate these things, that even when in principle these things can be estimated, they are often difficult to get a good estimate for, just because of all of the sampling bias. So, okay, this video is way too long, and so we'll call it good there.